Hello, everyone. My name is Erik Draeger. I am the Deputy Director of ECP's Application Development Focus Area, here to talk to you today about some of the lessons learned from the application side of things from ECP. I would like to call out Andrew Siegel, the Director of Application Development, who I've worked closely with during the course of this project. And I would like to walk you through briefly some of what we've seen and learned in this fascinating exercise. All right, so if you're familiar with ECP, you're aware that we have a fairly large application portfolio. And what I've shown here is just some pictorial representations to mainly try and get across and capture the diversity of the types of science and the types of application codes that we included in this portfolio. And there's multiple reasons for this. One is, of course, the Department of Energy simply has a lot of priorities in terms of our need to understand science at all scales, whether we're down at the molecular and atomic scale or all the way up to cosmology and astrophysics. But also from the perspective of a project like ECP, there's a lot of value in making sure that your portfolio is very diverse. And so we want to capture a lot of different types of applications. And the reason for that is, while the project has a very large focus on making sure that the Department of Energy's capabilities are advanced directly, the ones that we included in this portfolio, we also want to use these application projects as exemplars for other code projects, because there's many codes out in the country and the world that are going to need to be able to use exascale resources effectively. And by having a diverse portfolio, we're enabling there to be, hopefully, a large number of applications that codes can use as sort of models for how they themselves might move their project to exascale. And so this really gives us a big opportunity to get a nice cross-section of scientific computing. Now, one thing I want to call out is we did not start from scratch. These are not codes that we wrote brand new. In fact, we started from established applications. We had 24 application projects and then 6 what we call co-design projects, and I'll talk about that more in a minute. But these are established codes. Each application project often consists of multiple codes. And so pretty substantial code base that we started from, many that had to support existing user communities. So it wasn't like we could, the teams doing this could just tear those codes apart, lay waste to them, and then rebuild them. Often they need to refactor them in place so that the capabilities that had already been put into place were not completely destroyed. So, and as I mentioned, we're covering a large range of science and engineering domains. But another thing I want to call out here is that these codes primarily started as MPI, or maybe MPI with threaded OpenMP on CPUs only at the beginning of ECP. So there was still, these codes were not designed for exascale hardware in any way. I'll also talk a bit about how we tasked these projects with measuring and tracking success. Every project had to define a domain-specific challenge problem that we would use as its final benchmark for how they were able to use exascale hardware. And we broke them into 2 categories: codes that were fairly established and had been ported to petascale hardware and were running well on that, were in our performance category. And they were tasked with simply primarily achieving a 50x or greater capability performance increase on the new hardware. But then we had our other category, which was codes that were trying to either do something completely new or build in substantially new capabilities for expanded science and engineering, such that the code in the form it was going to be did not exist at the petascale era. So we couldn't really do a direct measurement of performance, and it wasn't primarily what they were trying to achieve. So that was our capability category. And I'm going to speak to the results for both of those categories in a moment. But I also want to sort of talk about where we were and where we knew we were going from the hardware side. So ECP was not a project that was involved in the procurement of this hardware. This was done by another DOE project under the Exascale Computing Initiative. But we of course had to use these machines as part of demonstrating our capabilities and our success. And so what DOE was looking at back in before ECP was really a CPU everywhere, a CPU only world. So we were focused on getting as much parallelism as possible. So we had these blue gene machines moving into the Knight's Landing in architectures, but we didn't really have a lot of GPUs. And so as GPUs started to become part of the HPC landscape, they came only as NVIDIA GPUs. NVIDIA was really the pioneer in using GPUs for general purpose computing. However, we knew by the time we hit exascale, that was no longer going to be the case. There was going to be multiple vendors supplying our GPUs. We didn't at the start know which vendors or which specific architectures we'd be using, but what we did know is we could not just assume an NVIDIA-only world. And so we really had to plan for a diversity of accelerators, and we expect this diversity and uncertainty to continue in the future. And so a key aspect of this entire project was us trying to prepare for hardware that we didn't have a lot of details on, but that had very different characteristics in terms of the programming models that were native to those architectures and maybe the best way to run a code on them. So the ECP application developments really had multiple key ingredients. A lot of people, when they think about trying to take a code that runs on one type of machine and move it over to another, they think of that as a purely porting exercise. You just have to rewrite the code in a different programming model. Maybe you have to change some kernels. But in fact, what we see going to exascale is that you need a much more holistic approach to this. And so we broke this down into the science goal. We had to define really what we were trying to accomplish on the science side, not just think about kernels and code. There was a lot of algorithmic innovation that was required to move codes from the old hardware that we tended to run on to what we were looking at in the future. We did, of course, have a significant porting activity, but then there was also a significant aspect of integration with other code projects, and I'll speak to that more in a second. But first, let me just talk about defining the science goal, because that was a really important thing for us to do from the get-go. So I'm going to talk about this via an example. So one of our application projects was the ExaWind project. This is a wind farm modeling project. And the need for this project is I attempted to capture with a screen grab of an article, which is sort of representative of what people who do wind farms design and siting deal with, which is a single wind turbine is a very well-known beast that, you wind comes in, you expect it to produce a certain amount of energy by those blades turning, problem solved. But if you look at the interactions of wind turbines on other wind turbines, the amount of turbulence that they create that scrambles the air downstream, this can have a significant effect on the efficiency and the operation of those wind turbines. And so it's not at all clear the optimal way to lay these turbines out such that you minimize those effects and the overall field and farm can operate as efficiently as possible. And so this is essentially the need for the ExaWind project. Rather than trying to do this experimentally, because those wind turbines are very big and heavy and hard to move around, it makes a lot more sense to do an optimization computationally and then use that to build these fields effectively. So this team had a very complex problem that they ultimately wanted to solve scientifically. How do they define success? What is their target? In past projects, it would have been, not unheard of for the project to simply define a very simple benchmark of a fluid dynamics simulation in a simple box, or maybe a simple single turbine. They would have looked at how efficiently they could model that and then just assumed they could couple those together reasonably well. We wanted to ensure that all the difficulties of the science problem were captured in the metrics that we used to track this project. So they ended up defining a very ambitious problem, which was an actual full array of 4 turbines, and we said at least 4, but we ended up doing exactly 4, in a large 3 by 3 by 1 cubic kilometer volume of fluid with a large number of degrees of freedom. So that is something that at the start of the project, you cannot do on current hardware. We were not certain we could do it on exascale hardware. So there's a lot of risk involved in this, but what happens when you do this is from start to finish, every application team does not focus on trying to get a good score on the metric. They focus on making sure the science capability that they're going to use eventually is from start to finish as effective and efficient as possible. And so this is the motivation for that, and we feel it worked out very well in ECP. So algorithmic innovation ended up playing a really key role, and let me explain what I mean by that. So a lot of times when you think about moving code from different machines, you assume it's going to be the same exact code. It just has to be tweaked so that it'll make use of that hardware. But instead, actually, as you imagine, going from code that was designed for CPUs and moving it over to GPUs, which have a very different hardware characteristics, very different ways of using them as efficiently as possible. In fact, you really need to reevaluate how you're solving the problem and undo all the assumptions that you put into that code when you designed it for the hardware that was available at the time. And so there are inherent strong scaling challenges on GPUs, for example, so you don't necessarily want to try to strong scale your way to good time to solution, but in fact, maybe you want to be using more ensembles. There's lots of ways of increasing the dimension of the parallelism you need to feed the GPUs, fragmentation methods, ray tracing, and there's lots of subgrid and local physics models that you may have avoided in the past because they're computationally expensive and the balance was not good. But in fact, once you have that data on the GPU, you may be able to do those calculations very quickly because the data movement is relatively more expensive than it used to be. And then ultimately, even just changing the overall mathematical approach, using higher order methods, changing the type of model you use to do the sampling, for example, from a history-based to event-based. So there's numerous examples of this. And honestly, the takeaway really needs to be that not what specific algorithmic change was used in any of these projects, but that anyone with an application project needs to really critically evaluate it from the ground up to see if, in fact, you are attacking the problem from a way that makes sense based on the hardware that we have now and that we're likely to have in the future. So I'd like to just sort of share our final results for the Exascale Computing Project from the application side. So I mentioned we have this performance category. We call this is KPP1 is what we're referring to. That's our key project parameter. And in fact, of our 11 KPP1 projects, the ones with the performance target, 10 of them surpassed the 50x requirement. And the 50x really was not a simple, this looks like it was a very easy metric, but in fact, we started with machines that were roughly 20 petaflops in capability, and we knew we were going to have a machine with at least an exaflop. But most of our codes were not compute bound. So it was not at all clear that we would be able to even get over this line, let alone that the majority of the codes would go so far past it. But in fact, because of that algorithmic redesign, because of that sort of end-to-end analysis and rethinking of how we solve these problems, it turns out there are far greater gains available than simply moving from a machine to a machine and just harnessing the physical hardware speed up. And so that's an important takeaway that, there's a lot of performance to be had just from solving the problem thoughtfully for the hardware you're doing. And I also want to call out our capability projects. Again, very high success rate there. 9 out of 10 were able to demonstrate their exascale capability. This is both in our Office of Science portfolio as well as our NNSA portfolio. I've shown the pictures of these capabilities down below. And I want to just call out our co-design portfolio. So these were primarily mathematical libraries that are essentially very foundational. So for example, if you look at the upper left, that's our AMREX project, that's adaptive mesh refinement. This is not a library you think of in the traditional sense of an external API that you can call and get an answer for a very discrete piece of a problem. Instead, it really needs to be integrated within the application from the ground up. It's a very deep integration. And so this work was done in close collaboration throughout. And so these applications that use this co-design libraries got a major benefit because, by working with these experts in this specific domain, you were able to build your code on a very powerful foundation and ultimately leverage a lot of their implementation work in your application. All right, so let me talk about porting. This is, of course, ultimately an unavoidable step of moving to a new architecture. Now, one of the biggest questions we've gotten throughout the Exascale Computing Project is, what programming model should I use? I have this code, what should I rewrite it in, or what should I, have chosen from the get-go? So I'm just showing sort of 4 broad categories of programming models, and I'll talk about sort of which ones our applications landed on. The most obvious is the GPU-specific kernels. If you have an NVIDIA GPU, you could just use CUDA to move your data and do your calculations on the GPU. It tends to be very efficient. It gets good performance. However, you are now sort of wedding yourself to that specific architecture, or you're creating a situation where you have to have multiple versions of all your kernels, which creates a real maintainability issue. Another attractive model to people are the loop pragma models. These are things like OpenMP or OpenACC. This is both of those now have the ability to offload calculations to the GPU. They come with some challenges. I'm going to talk about an example of those in a minute. This is the most common portability strategy for Fortran codes, which don't have access to the GPU-specific kernels for all GPUs, and of course cannot use the C++ abstractions. Now, the C++ abstractions, I would argue, is probably the most popular in the people. Let me see how to say this. So, if you have a C++ code, or you can have a C++ code, I would argue that a best practice would be to explore one of these abstractions. So Cocos and Raja are the 2 that we primarily are speaking to in this. They were developed by NNSA Laboratories, and they were basically developed in response to this increasing hardware diversity that we saw coming for large codes, where rewriting and refactoring these codes on a regular basis was simply not feasible. So you need something really robust that allows you to change things under the hood without having to rewrite the science part. And so this is a very powerful approach and highly recommended. And then lastly, within ECP, we had the code design frameworks I just mentioned. Many of these code design libraries did the implementations on the different hardware platforms so that the application code didn't have to. So they would just simply use their APIs to the code design library, and it would just work depending on what system they were on. So as I mentioned, we're often asked, what should I use? And in ECP, we never really landed on a single answer. The most popular model, program model, in the graph on the right was the Cocos Raja C++ abstractions, but they were by no means a majority. We had pretty even splits for the others between native GPU, loop pragma, and the co-design offload. One trend we saw in programming languages was, as much as possible, people moved away from Fortran. This is not a slam on Fortran as a language, but rather sort of a pragmatic realization that vendors were prioritizing C++ and Python over Fortran because that's where they saw the market going. And so Fortran codes found themselves with fewer options. They found themselves with more immature compilers on newer machines. So if you have a large Fortran code, you may not have the option of rewriting it. But if you have a small Fortran code, you may want to reconsider whether you really want to try and stick with Fortran long term, just because we're seeing that support is more of a challenge. Now, in terms of the porting, I want to just give an application example, because I think this is really illustrative. I'm speaking to the QMC pack. This is our Quantum Monte Carlo code. It's a C++ code, and at the start of the project, they had to decide what programming model they're going to use for these new GPUs. They already had a working CUDA version that ran on NVIDIA GPUs, but they knew that wasn't going to work for the other platforms. So what I'm showing here on the right are 2 graphs, and I'm going to talk about, let me just talk you through those a little bit, because it's really important to understand what all these bars are. So on the top graph, you have these different blocks of bars, and those numbers on the bottom are different systems. So each block refers to a calculation, whether it's 16 atoms, 32, all the way up to 512 atoms. And the values are relative speed up or relative performance to that CUDA code I mentioned. And so this is on NVIDIA. This is the V100 GPU. And now each of these bars represents an advance in the OpenMP offload runtime and compiler. So when they first started running their OpenMP offload code, it ran much slower than their CUDA code. And so you see that with the light blue bars there. And it was pretty true all the way up to the very, very large calculation of 512 atoms. But as they worked with the vendors and they identified bugs, or they analyzed their performance and realized that the runtime was not, offloading things the way they expected, they were able to see significant improvements. And so the different bars actually refer to different versions of the compiler and runtime. So this is really a time series, each one of these blocks. But the red bar is where they got to. And so if you asked, should I use OpenMP offload, it really is a very time-sensitive question. If you'd asked this team back at the beginning, they probably would have told you not to because it's much slower. But in fact, once the work has been done to, and again, this ends up being a very cooperative effort with the vendors and the compiler writers to identify why are they not seeing the performance they expect? What is actually happening under the hood? And in many cases, these are things that can be improved. And so the programming model really can vary quite significantly in the performance you're able to achieve, really just based on how it's implemented. And so the lesson here is, as long as you have people using it, and especially brave people like the QMCPAC team, who are one of the first people to use these architectures, you can really see major improvements. You can actually get a very robust runtime, but you have to make sure you understand what you're getting into as you make that decision. And new platforms may revert back to the light blue. And then just for some optimism, I'm also showing how they saw, what the performance they saw on the AMD GPU with ROCm, and that also became quite good. And again, that's still work in progress. They're still working through that, but it is the sort of thing that you are able to be very flexible and adaptive to these new architectures if you go in with sort of the right spirit of this is not going to be a one-shot build it, run it, see how it goes. And then last, I want to speak to integration. Software integration is something that historically applications that care about performance on leadership class HPC systems have avoided. The more libraries you have, the more dependencies, that's more complexity, that's more things that are outside of your control. As we enter the exascale era, that is completely the opposite. We are taking the opposite approach on that now. And fundamentally, it's simply because there's just too much to do yourself. You need to rely on expertise from others and specialists, who can really dig into these problems and solve them well. You need to leverage their expertise. So I'm just showing some categories of the types of, when we talk about integration, what we're really speaking to. We're talking about things like programming abstractions, but we're also talking about mathematical solvers and preconditioners, memory management, performance monitoring, in situ visualization analysis. It really runs the gamut. So here's sort of the big picture lessons that we learned about, integrating with software libraries and other codes. It is fundamentally not optional. The only way to ensure you're actually really making effective use of exascale hardware is to delegate as much of the key math and computer science operations to others. Another thing we found is that this needs to be developed and used, in close collaboration. It's very hard for libraries to develop all the capabilities an application might need in isolation and have completely abstracted APIs that they can just call and pull out results independently. So it's, the software developers need to understand the applications, what they're doing, how they're doing it, what they need. And then the applications need to really understand how the software libraries are meant to be used and ways they can be adapted for their specific use case. And one last thing we saw is that we should not be afraid of having multiple different implementations of the same capability from the software side. We actually saw multiple cases where competition really added value. So whether it was sparse linear solvers or the C++ abstractions, if there had just been one version of those codes, we would have worse performance or less capability than having two different teams working on the same area and coming at the problem different ways. They learned from each other, they competed with each other, one would outdo the other, and the other would work hard to catch up. And that really is an important driver. So don't there's some people get nervous when there's multiple versions. They would just want to maybe have the one blessed version, but in fact, there is a lot of good there. And let me just give a few more detailed examples of when I talk about integration. And these are mostly going to be on the math side, because I've already spoken to the programming models, and we're early days in terms of things like performance analysis and visualization. But it really does come down to, Exawind really needed efficient sparse linear solvers. And this is where the competition aspect came in. They had access to both Hyper and Trilinos, and at different points in the project and for different types of problems they were solving, one or the other library can, in some cases, would be significantly better than the other. And that helped both Hyper and Trilinos improve. QMCPAC really needed efficient batched dense linear algebra kernels. Our power grid optimization needed sparse indefinite solvers. This was actually a very big challenge. These are very difficult things to run well in GPUs, and so ECP invested in developing of those solvers. Our small modular reactor project needed custom discretizations that were specifically designed for these reactor assemblies. Our plasma Wakefield accelerator project needed a good mesh data structures and solvers. And our XFL project, the real-time light source analysis, needed non-uniform fast Fourier transforms. And so these are all things that ECP enabled, and honestly were critical pieces. None of these projects could have been as successful without those pieces. So I'd like to tie this all together by showing one of our sort of exemplars of impressive capability that was developed because of ECP. This is our EQ sim code. This is our earthquake modeling seismic hazard infrastructure analysis code. And so the starting point of this project was they already had a code, SW4, developed at Livermore, that had been developed and was beautifully designed. It was only written for CPUs, but also it was a code that you could tell it was written by physicists because it was designed to solve the mathematical problem in a very readable and intelligent way. The challenge is it was not written in a way that compilers could convert into efficient code. And so even on CPUs, the code was not running at a very high fraction of peak performance, not through any fault of the people who wrote it, but purely because there's a sort of a mismatch in what code looks like to people that in a way that's good and easy to deal with versus what code looks like to compilers. So they were able to, under ECP, rewrite this code into one of these C++ abstractions, Raja. And they also were able to take advantage of some of the software developed in ECP, including the ZFP data compression library. And ultimately, they achieved a 3,500-fold improvement in computational performance. And so that's not to say they were able to take a machine that had 50 times more flops and somehow run it past 100% of its peak performance, but rather they were able to undo all the inefficiencies because this abstraction layer was much easier to feed instructions to the compiler. But then they also used algorithms that were really well designed for GPUs. And the net combination of those was way above the 50x that we saw in terms of hardware capability. And so I'd like to show you some movies of the science that they're now able to do that they otherwise could not have done. So this is a model of the San Francisco Bay Area. The red dot is the location of a specific building shown on the right, and the star is the epicenter of a large earthquake that's on the Hayward Fault. And what you can see is because they're able to do high-resolution simulations, they now have access to the high-frequency components that would impact how a building, an individual building, responds in an earthquake. And so what we see here on the right is a three-dimensional model of a specific building. It's a fairly simple model, but you could imagine replacing with almost anything. And what we're seeing is how it would specifically respond to an earthquake at a specific location in this region. And so this is not the type of guideline you would give if you were telling someone how to build a building for seismic safety. You have to just sort of give broad guesses as to what sort of shear forces you're going to see. In this case, you have very specific information, very actionable information that someone doing building design could actually rerun. They could try a model. This is what we're planning to build, see how it responds to this earthquake. And if the shear forces or the deformation is greater than you're comfortable with, you could redesign that building and try again before you ever put a single bit of concrete or steel in the ground. And this is a game changer. This has never been possible before. Now, you may be asking yourself, well, that's great, but now I've built a building for one specific earthquake in one specific place, and it may not happen there. But because these projects were able to get their throughput, their scientific throughput, how fast they could run on these machines, they were able to get that so high, it's actually only a few hours to run one of these simulations on a big supercomputer. And in fact, what I'm showing here is 25 realizations, or rather, samples from 25 different realizations of earthquake all up and down the Hayward Fault. And they've also done it for the San Andreas Fault. And so now you can start to build out a real hazard map. And it's only because each one of these simulations takes a reasonable amount of time on, and they ran these on the Frontier supercomputer, but on, a leadership class machine, then in fact, you could really create, for any region where you have a detailed soil model, you could create a map that engineers could use to build buildings much more safely than was ever possible before, because they simply didn't have the data. There's no way to really know the nuances of different regions in a geographical area, how the waves are going to move through that soil and that rock and that topography into a given building. And so this is something I think is very exciting. And fundamentally is something that truly shows what Exascale can do, because this is not a thing that was possible before the Exascale project. And then just to close, I want to talk a bit about the future, where we're going. So most of the ECP applications, because they were faced with these 3 different kinds of GPUs, wrote their codes to be as portable as possible, and we're seeing dividends from that as they move from the Frontier supercomputer at Oak Ridge to the Aurora supercomputer at Argonne. Frontier has AMD GPUs, Aurora has Intel GPUs, so the simple fact they're able to move their codes over and run pretty quickly out of the gate is a real testament to them, to this portability strategy working. However, all of our current architectures are very similar. They are mixed CPU, GPU machines, and people tend to utilize them in terms of where the data goes and where the compute happens in a very similar way. But if you look to the right, these are the trends we're seeing for the future to get, ever increasing efficiencies in terms of power and heat and capability. Specialization continues to advance, and we're starting to see a lot of interest in true heterogeneity in terms of the different types of accelerators, the placements of memory, and then the way it's all packaged together. That's going to necessitate a much greater flexibility in how we write these codes. So we haven't really had to deal with heterogeneity before, despite the fact that we have both CPUs and GPUs. So let me talk about how we currently manage heterogeneity. So I'm showing a schematic of a Frontier compute node. So you have these 64 CPUs in blue, and then you have these 8 GPUs in red. And what we do now, so you have a lot of different compute power and you have 2 different memory spaces. So here's how we handle that. We take all the data, we put it in this HBM, the high bandwidth memory for the GPUs, and then we ignore the CPUs as if they don't exist. That's it. We do all the work here. This is not a heterogeneous computing example. This is essentially turning a heterogeneous machine into something as close to a homogeneous machine as we can manage, and then using that. That's great. That's a great way to do things efficiently, as we saw with things like EQSIM. However, we still are kicking the can down the road of how we're going to handle more advanced heterogeneity. And so again, I'm sort of repeating myself a little, but the motivation here is simply that when you have mixed CPU and GPUs, all the flops are on the GPU. So there's not a huge payoff to using those CPUs. We do see a bit of sort of modest heterogeneity, and I'm giving examples where it's more management and coordination, dealing with I/O and load balance. But I think there's going to have to be yet another sort of rethinking of how we do compute if more advanced heterogeneity comes down the line. I think it's something we need to be thinking about now. So just to wrap up, I'd like to sort of give our big lessons on how ECP was able to achieve exascale. Things on the left were sort of, I think, how people might naturally approach this as just a code porting exercise, or if you use software, just assume you can just sort of grab it off the shelf and just sort of plug it into your code. But as much as possible, just do everything yourself. In fact, this is not a porting exercise, but really requires a holistic rethinking and restructuring of the code from start to finish. We think that software is incredibly important, more important than it's ever been, and it really requires a close, tight collaboration between applications and software teams to be as effective as possible. And we really think that this has become a real community activity. You really need to be collaborating with others. You need to be talking to others. Working in isolation is a recipe for inefficiency and failure. So things like ECP need to happen again. Maybe at smaller scale, maybe different configurations, but the more we're talking with each other and working together, the more effective we're going to be. All right, so ECP, I think, was a really unmitigated success. It was an unprecedented opportunity. It was very exciting to be a part of. I think there's a lot other organizations can learn from this, but we need to warn people, this is just fundamentally a complex activity. Don't think that you can just sort of pull an ECP project and copy it and you'll be good to go. There's a lot of non-trivial effort that just is unavoidable. But I hope I've motivated the idea that it's worth the pain, because Exascale resources can truly provide a game-changing capability if you use them well. And more importantly, I think the hardware landscape is still changing rapidly and things are not going to get easier. So the more you start thinking of how to use accelerators, how to use different types of hardware flexibly and efficiently, the more likely you're going to be able to benefit from this rapidly changing landscape. So thank you very much.